Hello, in this video I'm going to show you how to model a water landing of a space crew capsule. This example requires several physics to be solved at the same time, and it is fairly complex. However, with a nice set of tool sets inside Ansys Workbench, we can quickly set it up and solve it. So let's dive in. The main objective of this example is to show you how these complex physics can be combined to create a more realistic and meaningful simulation of a real application. I'm using Ansys 2020 R1, which is the latest at this time, for my demo. It is 3D transient model with around 600,000 elements, which is coarse for most problems. We are also using Ansys HPC for distributed parallel processing to speed up the solve. Volume of fluid for the multiphase flow modeling is being used, and we set a dynamic meshing with passive walls and include a 6DOF solver to account for the capsule motion in 3D. The capsule will have a steady initial velocity of 40 feet per second or 12 meters per second. So here's a geometry that we'll be using. The capsule is here close to water. The bottom red is water, the blue is air. The capsule with an initial velocity come down, hit the water, and the water will splash and the capsule will slow down because of drag force. So the geometry is very simple, and we can use Design Modeler or Space Claim for it. You can also use any other CAD tool that you have. We're using Space Claim in this demo, and the capsule model was grabbed from open CAD databases. We'll be using Ansys meshing for the mesh, and it is a basic tetrahedral mesh with inflation layers around the capsule. For the motion, we will be using the 6DOF solver and the dynamic meshing. And for the multiphase flow, we'll be using the VOF model in Fluent. Then we set up the model boundary conditions and solve it, and finally post-process it in Ansys CFD. So let's go into the software and take a look at how we set it up. Okay, so here's my project setup. I have the geometry and mesh, and I have the Fluent model set up here, and finally the result. So let's look at geometry. I have it open here to save some time here. So the geometry has two parts, has the capsule and has the fluid domain around the capsule. And this would be water and air inside this fluid domain, and the capsule, of course, inside. So if you look at the capsule, you can see I have a sphere around it. This is a passive wall. And essentially what a passive wall does is that it acts as nothing inside the fluid domain. It's interior. The flow will go through it. But it allows us to move the sphere instead of the capsule, so we don't have to remesh the mesh around the capsule. The problem with dynamic meshing is that if you have to refine the mesh around the capsule with a lot of inflation layers, that would be a time-consuming process, and sometimes it could fail. So you have to tweak the parameters just to avoid certain issues. With this trick and having this passive wall around the capsule, you can prevent that from happening. Once you have that, you have to create a shared topology, so these two parts are connected, and that's all you have to do here. So once the geometry is ready, let's go inside meshing and take a look at the mesh. So geometry is a shared topology. You can see the capsule and the fluid domains here. We also have added a couple of things here. So around the aerodynamic motion of the capsule, we would like to capture that flow better. That's why we need to have better mesh around the moving part. And using inflation layers, boundary layers, you can create elements that are aligned with the flow, and that would help capturing the turbulence effects around this moving part. And you can see the sphere in there as well. So for the inflation layer, you essentially right click here, insert, and you can define inflations. And once you have that, select the body, and that's the capsule, and we select the walls. For the walls, I'm using a name selection. Rather than selecting the faces one by one, I have created a selection of, of the faces, call it named selections, and I use that in here. So just makes it a little easier. And later on, I use that as a boundary condition and also for dynamic meshing. Also, we would like to have more elements around the object inside that passive sphere, and I use a body sizing for that sphere to add more elements in there. Again, for your real problem, you would like to have more elements to increase your accuracy. For the demo, I'm using a coarse model, a coarse mesh, but around the object, you can see I have more elements, and I also have inflation layers around the object capsule itself to better capture the flow. So the name selections that we have also, one is for the fluid, as you can see here, and one for the passive wall and the capsule itself. So our mesh is good enough. We can also take a look at the quality and the number of elements, and if your sizing, everything is good. Again, just for the purpose of the demo, I have not created the best mesh possible, but it's good enough to show you how you set it up, a dynamic meshing and a complex sort of physics on a basic mesh. So now that we have a working mesh, let's go inside Fluent and see how we can set it up for this application. So the first thing we have to do, quickly take a look at your mesh. And Fluent, once you open it, will give you some information about the mesh quality. Make sure that is good quality. It has good quality for your application. And also just make sure the scale and everything of your calculation is appropriate with the physical model. So for this problem, we're doing a transient simulation. We also turn on the gravity because the capsule, it's essentially has some speed, but the gravity would be important in this case, just it's because it's a heavy object, and we need to include that in our calculation. So for the models, we have to do a multiphase flow, and we turn on multiphase here. And you can see volume of fluid and explicit. You can also use implicit, but explicit is more appropriate for transient problems. And in this case, we wanted to kind of get a more refined shapes of the droplets and the wave motion. That's why we're using explicit. Sharp, which is the default, and everything else, just keep it as default. We have two phases, water and air, and those phases are defined here. So water is the primary, and it's defined as liquid water. Properties of water are essentially, basic settings of water. And same thing for air, and you can see that here. So there is no interaction between the phases. Again, you could define surface tension or some other interactions between the phases. For this application, it's not necessary since the forces from drag force and the effects of drag force and lift forces and all the other forces are so large in comparison to surface tension, so we don't really need to include that. So that part is to setting up your multiphase flow. Next, we're going to look at our viscous model or turbulence model. In this case, again, we are using the default K omega SST model, and all the settings that we're using in this example are the default settings. You could go into more advanced models since we're doing transient, we could go even to large edit simulation or use higher order models. Uh, the the thing with that is if you're going to higher quality turbulence models, you have to make sure your mesh is appropriate for that. In our case, since we're using a demo sort of coarse mesh, uh, it's good enough. K omega SST is a good enough model to capture that, and we shouldn't really using any other models with higher order resolution since the mesh is not there. All right, and next we are going to set up the dynamic meshing, and for that one we have to look at a couple of things here. So the dynamic mesh is where you define the motion of the capsule. So the capsule has some initial velocity, and it's also a rigid body. So we define the motion as rigid body motion, but it can rotate in all directions. That's why we call it 6 degrees of freedom, and it can translate in all directions. So three XYZ directions for the rotation and also for the translation. That's why 6DOF is turned on here. And since the object moves, the mesh around the object, in this case around the sphere, that passive walls that we have around the capsule itself, the mesh will change. So we have to do some smoothing and some remeshing around that. Inside the capsule, inside the sphere around the capsule, we are not doing any kind of remeshing. And that's the whole purpose of having that passive wall around the object. So if you look at the settings, we're using diffusion as the smoothing method here. And for remeshing, a local cell. And these settings come from the mesh size. So I look at these numbers and the minimum scale, I usually use a smaller number compared to this, and kind of adjust the numbers based on what you see here. And this will help you as you're remeshing. You won't get elements that are skewed that would affect your accuracy and stability of your solution. And also you don't get elements that are divergent elements, and that will stop the simulation. Then for the 6DOF, we have to define a capsule, and here we define the properties, essentially the mass properties of the capsule. So here's the mass, here's the moments of inertia. I grab these numbers from mechanical. So basically you bring your model into mechanical, you can capture that. There are other tools to do that as well. So once you have the numbers, bring it here, you create the capsule, and you define the gravity direction. You can also save the motion history if you need it. Next is defining the parts that are actually moving. So here you can see I have capsule walls and I have the passive walls. And these are the rigid bodies that we have. So if you look at the settings here, so for capsule walls, it's a rigid body. I'm using capsule, which we defined previously. The velocity is defined here, and this is meters per second or 40 feet per second. That's the velocity of initial velocity of the capsule. And we define it at the center of gravity of the capsule. And everything else is set to 0. And this part is 6DOF is turned on the capsule. If you look at the passive wall, has everything similar to capsule, except it has the passive turned on. And that means the sphere is really just for meshing. We want to make sure that the mesh inside the sphere around the capsule is not remeshed, but anything outside the sphere is remeshed. And with passive, you're basically telling the solver that a flow can go through the passive wall, the sphere wall, can reach to the capsule itself, and also can be inside the domain. So again, the idea behind this is that we are not meshing inside the sphere. We are not, the inflation layers around the capsule and the mesh that is more refined around the capsule will be tricky to remesh every time and will be time consuming to do that process. That's why we're skipping that using this technique. So everything else, I'm using the default settings. So cell height would be better idea to set up your cell height based on your minimum height. In this case, I'm using 0 and the solver will pick the right one for me. So everything else is set here. We're ready to set up the methods and then solve it. Next, we look at the methods. So we're using simple, Presto, and second order for pretty much everything. And those are the basic settings for that. For the controls, everything using the basics, and these are the default settings. I'm not creating any report definitions, but you could definitely do that here, create monitors. But one thing we do need is creating a cell register. These used to be called regions. You used to mark a region. Now you create a cell register. Essentially, what happens is this. In this example, initially the domain is filled with water up to some height, and above it is air. The capsule is in the air and it hits the water. So one thing you could do in the geometry, you could have two separate domains, and the bottom one you basically patch it with water. The top one you patch it with air, but they are separate domains, and that's one way of doing it. The other way is to bring the model as one domain, as you can see here, and use a cell register to define a region that is water and a region that is air, and then patch those regions for initialization. Once you initialize it, then after that, water can go anywhere, it can go up and mix with air and vice versa. But initially, you have to set up the level of air and water to start the calculation. So to create a cell register, you basically right-click, create a region, and I've created one here. You define, in this case, y is the direction I actually care. So this is around 19 meters. So I did the quick calculation. So around 17 meters would be very close to the capsule. And as you can see, for X and Z directions, I'm using very large numbers, just minus 100 and 100. So basically, it will capture all the elements that are in those in the domain, and I say everything that is outside this area. So essentially, what I'm specifying with this region is air. That's the air location. So I can call this air domain. So we know what we're doing. And if you look at that, here's the domain that we are, the region that we are creating here. So once we have the cell register, go in initialization. And then here, I use the standard initialization for everything. And as you can see, initially it says, air volume fraction is 0. So maybe I set that to keep that as 0. And then we can set the volume fraction of air in the top region to be 1. And so if I initialize it here, and then I look at, click on patch, and I select my air domain, which is the same as test in this case, and I look at my mixture, and you can see here, and you have mixture and you have air, volume fraction of air, set it to 1, patch, and close this. Now, if you look at your contour plots, just kind of, to ensure that this actually worked, I have created a plane, XY plane, and if you display that, that will show you the sphere, the capsule is inside the sphere, see water is here and air is there. So that's a good starting point for our simulation. Next, let's look at our calculation activities. So Autosave, I've set it to 50 saves every 50 time steps. Save that, and then I can create videos and animations of the flow. Everything else is good here. I don't have any commands to do anything extra here. And the solution animation, I'm not using Fluent animation option. I'm going to use it in CFD post option to do that. So I'm saving my data here. I'll do a post processing and creating animations in CFD post. So for this calculation, I am using fixed time stepping, again, basic, but you could use adaptive. Adaptive is also very useful in this case. The reason I used fixed was really to simplify the problem and also be able to create animations a little faster this way. You don't have to match the time steps this way. So the time step size is 1 millisecond. As you can see, it's small, but it's important to have a good time step for your application, since we have dynamic meshing and we also have multi-phase flow, and impact of the capsule with the surface and the meshing and all the dynamics that are happening during that has to be captured. So you may even end up using a smaller time step to avoid any kind of issues. So when everything seems to be fine here, we can start the calculations. So I let the simulation run overnight, and once you bring it into CFD post, you can create a contour plot of it. And here I'm showing you the contour plot of VOF, volume of fluid. You have air on the top and water in the bottom. The capsule is here. You can kind of see that passive sphere around it because the mesh inside hasn't changed. And if I play this animation for you, you can kind of see the interaction. So as the object moves, it is remeshing and it's also solving at the same time. So here's another animation of the flow. You can see it from different angles, and you kind of see water in the bottom and air on the top. The capsule enters and the drag forces slow it down. You can see the water splashing. So that's the volume of fluid working. And you can also see that it's moving in all directions. So that's the 6DOF solver. And I showed you the moving mesh in the previous slide. I hope this quick demo was helpful to you. If you have any questions, please let us know. Thank you.